Eklavya, who is a PhD student at UIUC. Eklavya did his bachelor's from Learning. Then he worked in the industry with media.net for 1 year before joining IISc for master's. During his master's, he worked on several variants of one-dimensional filters. In the rarity, his master work produced 3 publications, 1 in approx and 2 in Epistemic EFX, for one of which he is also the solo author. Apart from this, he is also an expert developer. So he is currently at UIUC doing his PhD with Professor Eklavya. His present work focuses on pair division, and that is going to be the topic of the talk. In particular, we will be talking about epistemic EFX allocations.
Thanks, Kevin, for the introduction. Today I'm going to talk about pair division. In particular, I'll talk about epistemic EFX allocations. So I'll start by talking about the pair division problem for goods. Okay? So in this problem, there are a lot of goods that we want to divide among n people, and I'll call these people agents. And the agents are equally deserving, which means that we want to divide the goods in such a way that we're not discriminating against anyone by giving too much to one agent or too little to the other. So there are mainly 2 versions of this problem. There's a divisible version where we're allowed to cut some of the goods into pieces and then divide the pieces among the agents. And there's an indivisible version where we cannot divide a good into multiple pieces. That is the indivisible version, also called the discrete version of this problem. Okay. So when the goods are so this problem is trivial when the goods are divisible and they're homogeneous. We just cut them into equal sized pieces. The problem becomes more interesting when different agents have different preferences for different parts, for different goods, or for different pieces of the goods. So in the case of indivisible goods, like some applications are pair division of inheritance and divorce settlements. And when I was a little child, I used to do a lot of pair division with my sister for toys and candy. And in the divisible case, in the divisible case, cake division is the general term that's used for a standard version of the problem. And of course, the applications include land division or division of radio frequency spectrum or airplane runway time. Let's now formalize the problem. We have a set n of agents where I'll denote the agents as integers from 1 to n, and we have a set m of goods. In the indivisible setting, we denote the goods as integers from 1 to m, and in the divisible setting, we can assume that there is a single good that is a subset of the real line that is an interval from 0 to 1. And for each agent I and every subset S of goods, we have a quantity called the valuation of that set for agent I, which I denote by Vi of S, and that is a non-negative value. And we call this as agent I's valuation for set S. Okay. So we assume that the empty set has valuation 0, and there are a few more natural assumptions that we make. For instance, if S is a subset of T, then the valuation of S is less than or equal to the valuation of T. And in a lot of works, we also assume additivity, which means that if S and T are 2 disjoint sets, then the value of the union of these sets is equal to the sum of the values of S and T. Okay. And for indivisible goods, additivity basically means that the value of a set is the sum of the values of the items that make up the set. And an allocation is a partition of the goods into n pieces, which we call bundles, and we formally denote it as an n tuple, where each element of the tuple is a subset of the goods, such that all of these sets are pairwise disjoint, and their union is the complete set of goods. And so here xi is called agent i's bundle in allocation X, and our task is to find an allocation that is fair. Let's now look at some notions of fairness. So one very popular notion of fairness is called envy-freeness. Okay, so in allocation X, we say that agent I envies agent J if agent I's valuation for J's bundle is more than her valuation for her own bundles. Okay. So here I have an example where there are 3 goods and there are 2 agents, Alice and Bob. And in each cell in this table denotes the value of that good for that agent. Okay. So consider the allocation where Alice gets the candy and the cookie and Bob gets the lollipop. So this is an envy-free allocation because Alice's value for her own bundle is 6 and her value for Bob's bundle is 6. So Alice is envy-free, and Bob's value for his own bundle is 25 and his value for Alice's bundle is 20. So Bob is also envy-free. Okay. For divisible goods, it has been shown that an envy-free allocation always exists. And this is true even for non-additive valuations. Okay. For indivisible goods, an envy-free allocation may not exist. For example, if there is a single good and there are 2 agents, then whoever does not get the good will be envious. Okay. So in this talk, I'll mostly focus on the additive case of additive valuations, and I'll explicitly state if I'm talking about non-additive valuations. Okay. There's another notion of fairness called proportionality. And we say that allocation X is proportional if an agent's valuation for her own bundle is at least her value for the entire set of goods divided by n. And if this is true for every agent, then we say that the allocation is proportional. And so this allocation here from the previous slide, we can show that this is also a proportional allocation. In fact, when valuations are additive, an envy-free allocation is also a proportional allocation. So again, for divisible goods, a proportional allocation always exists, and this is true even for non-additive valuations. But for indivisible goods, a proportional allocation may not exist. For using the same example of 1 good and 2 agents. So in the divisible setting, we see that envy-freeness and proportionality seem like very natural notions of fairness, and they exist. So they seem to be good notions of fairness. But for the indivisible setting, it's not clear not immediately clear which notion of fairness we should use. Okay. So let's try to look at a simple example that would motivate notions of fairness. Let's say we have m identical goods and there are n agents, and so apparently the most fair way of dividing items is that each agent should get either floor of m by n goods or ceiling of m by n goods. So let's see how can we generalize this idea. Okay. One way to do it is using the notion called envy-free up to any good. So the key observation here is that in the allocation, in this example allocation, you pick any 2 bundles, they differ by at most 1 good. So this is this is the key observation here. Okay. So we say that agent I strongly envies agent J if even after removing a good from J's bundle, agent I still considers J's bundle to be better. Okay. And we say that an allocation is EFX is no one strongly envies anyone else. So here I have a fair division instance where Alice gets the lollipop and the cookie and Bob gets the candy and the donut. And so if we look at Bob, okay, so this is the allocation that I've drawn on the left side. On the right side, I've drawn what I call a summary table, which tells us what's the value of each bundle for each agent. So here we can see Bob's value for his own bundle is 29, but his value for Alice's bundle is 28. So Bob is envy-free, but Alice is not envy-free because Bob's bundle has greater value. But she does not strongly envy Bob because if we take any good out of Bob's bundle, then Alice will favor her own bundle. So naturally, 2 important problems arise that do EFX allocations always exist, and can we efficiently compute EFX allocations? So what we know so far is that EFX exists when there are 2 agents or when the valuations are identical, and this is true even for non-additive valuations. This is a fairly simple. Okay, this is not a very difficult result. Okay, and it was shown recently that when there are 3 agents, even then EFX allocations exist. Okay, but when there are at least 4 agents, then this problem is still open, and it's been open since 2016. Okay. So for this reason, there are a lot of relaxations of EFX have been studied. for instance, EF1 or alpha EFX and EFX with charity. Actually, EF1 was studied even before EFX, but yeah, anyways. So alpha EF, so I won't talk a lot about those relaxations, but I'll mention alpha EFX briefly. So we say that an allocation is alpha EFX, where alpha is a constant between 0 and 1. If agent I, if after removing any good from J's bundle, agent I's value for her own bundle is at least alpha times the value of J's bundle. And when alpha is equal to 1, this is the same as EFX. So the best known result here is that in polynomial time, we can find an allocation that is approximately 0.618 EFX. So that was envy-freeness up to any good. And so that was like a...
That was for them.
Yes, that was for all. For n greater than or equal to 4. The previous slide, I think was for alpha EFX, I don't know of any better special cases. So EFX was a relaxation of envy-freeness. Now we look at a relaxation of proportionality. So proportionality is basically a threshold-based notion of fairness, that every agent I has a threshold mu I associated with them, and they consider the allocation to be fair to them if the valuation of their own bundle is at least that threshold mu I. Okay? For proportionality, this threshold is the value of the entire set of goods divided by n. But for MMS, we use a different value. So this is how the threshold is computed. We ask an agent to divide the set of goods into n bundles and then picks the bundle that has the minimum value for them. Okay, and that, so now there are multiple ways of dividing the goods into n bundles, and we assume that the agent wants to maximize their own value, so they'll do it in the best way, which is why, so this is how we get this expression here. Okay. And we say that an allocation is MMS if every agent gets their MMS threshold. So in this example here, it can be shown that for agents, the first two agents, their MMS threshold is equal to 1. And for the third agent, their MMS threshold is equal to 10. Now again, we have the same questions, that do MMS allocations always exist and can we efficiently compute them? Okay. So when all agents have the same valuation functions, then an MMS allocation exists. But even for this special case, and even when there are only two agents, it is NP hard to compute an MMS allocation. Okay. And there is a known example with three agents, or with at least three agents, for which an MMS allocation does not exist. Okay. So for this reason, people have studied relaxations of MMS. So the best known relaxation is alpha MMS, where alpha is a constant between 0 and 1. Our aim is that every agent should get at least alpha times their maximum share. And the best known result is roughly that each agent can get 3 by 4 times their MMS, and we can do this in polynomial time. So we've seen two notions of EFX and two notions of fairness that have been derived from envy-freeness and proportionality, EFX and MMS. But the results here are not as good as what we got in the divisible setting. So these notions have limitations. For example, MMS allocations don't always exist. And the existence of EFX allocations has been an open problem for a long time, which means that they may not exist. So first of all, I mean, I sincerely hope that EFX allocations exist, but if they don't, then we need a contingency plan. Okay. And maybe like these limitations indicate that maybe EFX and MMS may not be the right notions of fairness to focus on. Maybe there's some other notion of fairness that doesn't have this limitations, but is intuitively very fair. Okay. Now, what would such a notion of fairness look like? In fact, what does even fair mean? It's hard. So it's a very subjective but philosophical question, but I think it's an important question to ask. Now I'm going to present a notion of fairness, but I'm not claiming that my notion of fairness is that perfect notion of fairness. Just a disclaimer. Right, so let's see what a good notion of fairness would be like. So one idea that I had is what I call the mind your own business principle. Okay? So the idea is that whether an allocation is fair to you should only depend on what your bundle is. Okay? So we formally express this like this, that consider that there are two parallel universes, and in the first universe we divide items according to allocation A, and in the second one we divide items according to allocation B, and agent I gets the same set of items in both the universes. And then we ask this agent, is this allocation fair to you? And if she gives different answers, then it means that the notion of fairness that that agent has in her mind, that violates the mind your own business principle. Let's see which notions follow the mind your own business principle. So all the threshold based notions. Yeah, so there are two allocations in each universe, and agent I gets the exact same set of goods in both of these. Okay? And in each of these universes, we ask that agent whether this allocation is fair to them. If they say yes in one universe and no in the other, then it means that the notion of fairness that they have in mind does not follow the mind your own.
All allocations here, person gets the same items in all, and you like commute all other animals over to all universes.
Yeah, what I'm saying that if that even if we distribute the item, we redistribute the items that the other agents have, that should not affect you. You should only worry about what you have.
It's not really a particular fairness notion, but
Yeah, true. True.
So, are you able to show something about any fairness notion that satisfies this?
Yeah, that's what I'm going to talk about in the next slide.
Can there be any mind your own business stuff which is not threshold?
Yeah, the notion of epistemic EFX that I'm going to talk about does follow the mind your own business principle.
Just to like get it formally, what you're saying is if I deem some allocation A to be fair for a fair division instance, and then any allocation deem it to be fair for some agent I, then any allocation B where AI is equal to BI should be deemed fair for I.
Yes. So all the threshold based notion. Okay. I've never come across this notion before. Maybe it uses a different name.
So it's called non-counterfactual. Yeah, it has a. It's not. It's been looked at. It's called non-counterfactual simulations. It has a specific name in mathematics, not in like discrete case, but yeah, markets is looked at. So you never do a counterfactual analysis. You don't say, oh, had it been this or had it been that. So
yeah, there's a term for matching also for choice rule. I can't remember it, but it's something like you don't look at other alternatives to verify that this property is satisfied. You don't need to look at other possibilities or like other people's allocations.
Okay.
yeah, it's you search for something like non-counterfactual matchings. You should be able to. But it's just it was fair. It's not a. So the matching instance, like the context is different.
Okay.
It's a much more Latin heavy phrase than mind your own.
Okay.
Okay. For two agents, EFX is MIOB.
Yes. In fact, for two agents, if there are only two agents, then any notion of fairness follows the mind your own business principle.
For additive.
Yes, for I mean, no, I mean, if there are only two agents, then you can't really redistribute the goods and
You can have more constraints like capacity or something, then
Charity,
charity will come then.
Yeah, true.
You don't have two universal if you have just two.
Like there's no alternate allocation while you're getting the same set of allocations.
You can use charity.
You could have charity. Like you could throw away some. Oh.
So EFX violates the mind your own business. For instance, let's say we have this allocation here where according to Alice all the goods are identical. Now there is this another allocation here where where Charlie gets 5 items and Bob gets this one. Now here Alice would strongly envy Charlie. So so even though Alice has the same set of goods in both allocations, she is happy with one and not happy with the other. So EFX violates the mind your own business. But violating the mind your own business principle doesn't mean that this notion of fairness is bad. It means that the notion is perhaps too strong, that not only does it guarantee that every agent gets a sufficiently large share, it also mandates that according to that agents, the rest of the goods are almost roughly equally distributed among the rest of the agents. Now, EFX also has another problem which I call instability. I'll explain this with an example. Let's say we have this fair division instance with us where we have 9 goods. Okay. Let's say Alice likes chocolate, so her first preference is this bar of chocolate, and her second preference are these chocolate chip cookies. Let's say Bob likes hard candy, so his first preference is lollipop, and his second preference is green candies. And let's say Charlie likes to eat healthy, so his first preference is this watermelon, and his second preference is anything that contains chocolate. Okay. So if we consider the allocation where Alice gets the bars of chocolate and the green candy, and Bob gets the cookies and the lollipop, and Charlie gets the watermelon. So this is the summary table for this allocation. And here we can see that this allocation is actually an envy-free allocation, and so it's also EFX. Okay? But Alice and Bob, after looking at each other bundles, realize that they can swap some items. So they do that. And in this allocation now, both Alice and Bob are better off. Their valuations increase from 102 to 120. But now Charlie strongly envies Alice because according to Charlie has a value of 25, but even if we remove a bar of chocolate from Alice's bundle, it should still have a value of 30. In fact, this allocation is not even EF1. Okay. So it means that we started out with an EFX with an allocation that has very strong fairness guarantee, but this agents swapped some good amongst themselves, and now this allocation is doesn't satisfy good notions of fairness, and which means that there may not even be a point in spending so much computational resources to get a good notion of fairness if it's eventually going to degrade into something that's not fair.
What is the definition of stability in this case?
So I've not formally defined it, but intuitively it means that some agents swap items among themselves, and
Some subset can solute and then they can make it non-fair.
yeah.
Technical improvements can violate the fairness.
Yes.
That's what you said.
Yes.
Based from it improves Pareto twice and still the fairness property got killed.
Yeah. Yeah. Okay.
EFX allocations are not unique.
Yeah, they're not unique. There are other.
Even when they exist.
When they exist.
Yeah, I mean, for this specific instance, they are not unique. In fact, some EFX allocations are stable. If you look at this EFX allocation, this is stable. Like if you try to somehow make agents swap items, it's not going to work because this.
So towards like motivating your definition, are there no examples where no EFX allocations are stable?
No EFX allocations are stable.
Like in this example, there is some EFX allocation that is stable.
Indirect way, yeah. there are examples where there is no EFX and PO allocation, which means that for any EFX, you can move to a PO1 EFX as well. So the entire Pareto frontier is devoid of EFX also.
Oh.
So that in a very sort of.
But I guess that's, I mean, that does that assume that some goods have zero valuation?
I think it does,
Yeah, I've had a discussion with Professor Jugal, and he said that all the examples that show that EFX plus PO may not exist, all of them assume that some goods have zero valuations.
or they're beyond additive value.
Yeah, something like that. Yeah.
We do allow for that zero value. It's a very non-explicit answer.
So in fact, this is how we formalize this notion. We say that an allocation A Pareto dominates an allocation B if it's if for some agent if some agent is better off in allocation A and all the other agents are not worse off in allocation A. Okay, and we say that an allocation A is Pareto optimal if A is not Pareto dominated by any other allocation. So basically, if an allocation is Pareto optimal, then it means that a subset of agents are disincentivized from rearranging goods among themselves. So yeah, EFX plus PO is whether it's an open problem or not depends on whether you consider this special case, whether you consider this case of goods having zero valuations as a good example or not.
The previous thing that you mentioned, like not the instability, but so in that, mind your own business principle, that's not even satisfied by EF1.
Yeah, true.
Then EF1, you can rearrange other bundles and
Yeah,
calculate the EF1. Right? In fact, any interpersonal comparison is off the table if you try to mind your own.
I guess I can't see a proof of it, but like, intuitively it seems like it should be good. Okay. So we think about using Pareto optimality to somehow fix this instability, and then that will actually make this problem even harder. Getting an EFX allocation by itself is so difficult, and if we impose Pareto optimality, that will make it even more difficult. So we look at it from a different perspective. Okay. So let F be any notion of fairness. So F could be envy-freeness or EFX or EF1, whatever. So we say that an allocation X is, satisfies the notion of fairness called epistemic F. If for each agent I, there is an allocation Y such that agent I gets the same bundle in both X and Y is fair to agent I according to the notion F. Okay. And in this case, Y is called agent I's certificate of fairness. So in this example, let's take this example. So this allocation is not an envy-free allocation because, like, assuming that according to Alice, all these goods are identical, then Alice would envy Charlie. But there is this other allocation where Alice gets the same set of goods, but we can redistribute the goods such that Alice does not envy anyone. So this allocation Y is envy-free, and for this reason, allocation X is epistemic envy-free, and Y serves as a certificate of that. So here, an allocation Y, we have this allocation X. X is not envy-free. We have another allocation Y, and Y is envy-free. And in both X and Y, Alice gets the same set of goods. So Y is an envy-free allocation, and so Y is an envy-free allocation, and Alice gets the same set of goods in both X and Y, and so by definition, X is an epistemic envy-free allocation to Alice.
And you have to have such Y for every.
Yes, we need we need to show a certificate, such a certificate for every agent, and different agents can have different certificates.
In other words, like saying there exists a redistributions of goods besides xi, such that I consider now under this hypothetical data universe thing, I would consider it fair.
Yes.
The idea is I can see my bundle and I know what goods I have not got. So if I can envision some fair distribution for me, then I'm happy.
Yeah.
It's all threshold-based allocations, like epistemic does not make it. Like it's the same.
Yeah. Yeah. All allocations that satisfy the mind your own business principle, for them, F is the same as epistemic F.
The non-epistemic business example.
There is a what?
Example where it's mind your own business but not epistemic.
Mind your own business, but not epistemic.
Or is epistemic attempt to formalize mind your own?
Yeah, I mean, if for epistemic F as a notion of fairness always follows the mind your own business principle. And I think there is, if F is, what was the question?
Which is not epistemic, but still mind your own business.
Epistemic is a way to convert any fairness function to obtain.
Okay, formalization.
I think it is because if you take the fairness function itself, then its epistemic version is.
Yeah, if an allocation, yeah, if it follows the mind your own business principle, then it's the same as its epistemic version.
Repo improvement always preserves. Like what there can't be some fairness such that the epistemic fair plus the voice. But it should arbitrarily should be possible.
I'm not sure about this. Like maybe it's possible that I can shuffle around the goods of everyone such that Alice's bundle now has more valuation, but now she starts.
Not fair according to
Yeah, I guess it could be possible.
But you're poor, you never envy. As soon as you become rich, you start envy.
Yeah.
EIXI is less than 10, I do not. Yeah, but envy towards anyone else is 10 minus EIXI. Science EIXI.
Okay.
So when you say predisposition, it's just it's like a Boolean relation. You're an agent and an allocation. F says whether it's yes or no.
Yes.
So I could, like in principle, formalize fairness solution as just a collection of agent comma partitions.
I think yes. Okay. Okay, so very, I do somehow have the feeling that it's similar to MMS, but I don't really know in what. So in an epistemic EFX allocation, different agents can have different certificates, and an epistemic F allocation follows the mind your own business principle, and if F already follows mind your own business principle, then it's the same as its epistemic version. And epistemic F is a relaxation of F, but perhaps it's almost as good as F. So I and Professor Jugal got the idea for epistemic EFX sometime around when I started my PhD. And later we found out that epistemic envy-freeness has been studied before, and they were the ones who coined the term epistemic, so we're just going with that terminology. Frankly, I don't really know what this word means. Okay.
Greek words, I guess. So, possibly someone can include the Indian term. I have an example of that.
So in their paper, they introduced epistemic envy-freeness, and they left the question of whether epistemic EFX exists or not as an open problem. So what do? We have a fast polynomial time algorithm that computes an allocation that is epistemic EFX and is also 2/3 MMS. And we show how epistemic EFX is related to some other notion of fairness. We show that an MMS allocation is also an epistemic EFX allocation, and this is true even for non-additive valuations. We show that an epistemic EFX allocation is also a 4/7 MMS allocation. We have a few more related results of this kind. And most of our work was independently discovered by 3 others, which is Karagianis, Nidhirati, and Giovanna Varicchio.
This is for additive valuations, the first bullet point.
The first, yes, yeah, this is for additive valuations.
If you set 2A, then by the existing 2-third MMS allocation is
Yeah, approximate MMS need not imply approximate epistemic EFX or something like that.
For like particular valuation classes for which MMS is known. Like grant functions, MMS exists, so I directly now know that epistemic EFX exists.
Yes. Okay, actually there's a slight catch here that when some items can have 0 valuation, then this does not imply, but yeah, I just brush that under the rug. Let's see how do we compute epistemic EFX allocation. So we
Just to sort of anchor my epistemic EFX would mean that I have a partition where I look at every agent, look at xi, then I can redistribute v at all the remaining goods so that I have EFX.
Yes. Oh, so that you can redistribute all the goods among the others such that
Redistribute hypothetically.
Yeah, such that that agent does not strongly envy anyone.
Under this hypothesis.
But the other agent can
Epistemic only requires this exercise for each. You go home, you put your door, you say, okay, it's a world where there was no Adani and Adani. Well,
Okay.
So you will study this EEFX1, EF1, epistemic EF1 kind of works in that book, or does it make
I think we already have good results for EF1, so for that reason.
but EF1 would imply epistemic.
But those cases where you don't have any EF1, then
Or create computation of EF1.
Okay. So we solve this problem in 2 steps. We first reduce it to a special case, which we call ordered instances, and then we solve that special case. And in a paper by Professor Siddharth Burman and by Krishnamurthy, they used a similar 2-step approach to get 2/3 MMS. So we also use the same approach. In fact, we use the exact same algorithm. Okay, and so in their paper, they give an efficient algorithm to compute an EFX allocation for ordered instances. Okay, so the second part is actually already done. We just need to focus on the first part. So we say that a fair division instance is ordered if everyone's favorite item is the same, everyone's second favorite item is the same, and so on. Okay. So in a sense, ordered instances are a worst case scenario because let's say there are n agents and n items and everyone's favorite good is different. Then you can just give everyone their favorite good and it'll be envy-free. The problem comes where everyone's favorite good is the same and they all start fighting. Let's look at what the algorithm is. for an input I, we first compute an ordered version of it. Okay. So, for input I, we have we denote the ordered version by I hat. So intuitively, it's this thing that we look at each row and then we sort it in decreasing order. That's how we get it. And more formally, we create a new instance with the same number of goods, and the good GJ has, for every agent I, the value of GJ is their value of their jth best good. The next step is that we find an EFX allocation of I hat. So Verman and Krishnan will be already give a fast algorithm for this.
How do you compute I can?
We just sort all of these. So we have this list 3, 2, 10, 11, 1. We sort it in decreasing order. So we get 11, 10, 3, 2, 1. And we do this for every agent.
That rows will have the same.
What do you mean?
It's a different. G1, G2, don't mean anything.
Yeah, so this is one instance and this is a different instance. So we're using the instance I to create a different fair division instance I hat.
It's an analytic tool. No semantics to the GI.
We could have used any row to order, get the second ordered arrangements.
Ordered all the rows.
All the rows are ordered. That's why it's not, G1 is not a good from those.
Yeah.
Okay. It's just saying what is the value of your most preferred good, what is the value of your second most preferred good.
Yeah. Now, step 2 is that we find an EFX allocation of this ordered instance. So here I have the same example, and if you look at this allocation, then yeah, we can see that this is an EFX allocation, but let's not spend time on verifying this. And the third step is that we create a list A of agents, and this list can have duplicates, where AJ is the owner of GJ. So in this list, G1 goes to Alice, so the first element of the list is Alice. G2 goes to Bob, so the second element of the list is Bob, and the third, fourth, and fifth elements of the list are all Charlie. G1 and G3 can be.
G1 doesn't mean one particular object.
Yeah, I mean, it could be possible that agent 1's favorite good and agent 2's third favorite good are the same in the original instance. So this list A that we create, this is called a picking sequence. Now we place all the goods in the pile, and then we call the agents from the list A one by one, and we tell them to pick their favorite good and take it away. So this is what they do. First, Alice goes, she picks the bar of chocolate because that's the favorite good. Then Bob comes. When Bob arrives, there are only 4 goods in the pile. Bob's favorite item is the lollipop, so Bob picks that, and there are only 3 goods left, and then Charlie picks them all one by one.
Why did Alice get the priority?
So that's because that's how we created the picking sequence in the previous step. Okay.
Think of GIs as the yeah. So if you're getting G1, that means you get to pick first. If you're getting G2, you're going to get G is like the rat in a tree. It's how high you get to pick. Okay. So if you're getting G3 equal G5 means you get to pick third, fourth, and fifth time. Okay. So where you're positioned in the queue.
So that's what you're meant to pass.
Yes. Hence the word picking.
Yes.
So here, in EFX allocation is I hat. You get an epistemic EFX allocation in the original, right?
Yeah, that's what we'll show you.
Yeah. Is there there can there exist? So there could be multiple EFX allocations here, and that determines a between sequence.
Okay.
And that would give some epistemic EFX allocation.
Okay.
So there is this like one-way mapping. But is there a mapping the other way? If you show a epistemic EFX allocation in the other instance, is there a way to?
Oh, you mean can this algorithm give you every possible epistemic EFX by
the count same number of epistemic.
I don't know. This is what happens. Agents come one by one and they pick their favorite remaining item when it's their turn. Not sure about mind your own business fairness notions in general, but for threshold-based notions of fairness, this is true. Yeah, this would improve, and so it's a mind your own business. Okay, so wait, what's your question?
I think any fairness that satisfies mind your own business principle, we should be able to reduce these ordered instances and solve that. And that would end up worse.
Not sure of that. I mean, it could be that you pick a different set of goods in the original instance, which is better according to you, but maybe the remaining agents got something that is. I mean, you don't just care about your set of goods, you also care about what everyone else gets. Even for mind your own business fairness notions where it satisfies the mind your own business principle, you don't worry about how the rest of the goods are divided among the different agents, but you may care about what that entire set of goods is. Yeah. So this is a summary of the algorithm. We first compute an ordered instance. Then we find an EFX allocation x hat for the ordered instance I hat. Then we create a picking sequence. And then we call agents in the picking sequence order and allow them to pick their favorite remaining item. And now we're going to show that the output of this algorithm is epistemic EFX. The fourth step? Yeah, I mean, yeah, which means, I mean, the picking sequence has length m, so basically m times agents will come and each time they'll pick one item. So let's see, why does this work? So let x hat be the EFX allocation of I hat and let x be the allocation of the original instance output by our algorithm. Okay. Now suppose agent I got goods G5, G10 and G13 in the ordered allocation x hat. Okay. Now suppose agent I gets goods A, B and C in X, okay, then we can show that the value of, let's assume that A is the most valuable, then B is the next most valuable, and then C. Okay. So then we can show that the valuation of A is greater than or equal to the valuation of G5, valuation of B is greater than or equal to the value of G10 and so on for agent I. And the reason for it is this, that agent I picks in rounds 5, 10 and 13 because that's how we define the picking sequence. It's based on what they got in X hat. Okay. And then at the beginning of round 5, 4 items have already been taken. So among the top 5 items in the original instance, at most 4 could have been taken. So they'll always get something from the top 5. So when agents come to pick up items one by one, in the 5th round, 4 items have already been taken because, okay, so in the original instance, suppose an agent had, considers their top 5 goods. Okay? Now, if 4 items have already been taken, it means that out of those top 5, at most 4 could have been taken. So if they pick their favorite remaining good, that will be in their top 5. Similarly, when they come to pick in the 10th round, they'll get something from their top 10. Yes. So let's see how we can formalize this idea. So for two sets S and T of goods of the same cardinality, we say that S dominates T if, according to agent I, if the jth best good in S according to agent I is at least as good as the jth best good in T for all j. Okay. So this gives us a mapping from T to S where for every good in T, the corresponding mapped good is either better or equally good. So the first result that we have is that xi dominates x hat of I, which means that when we go from the ordered instance to the original instance, according to agent I, every good will get better or be equally as good.
I mean, it does not make sense to compare the allocations of xi and xi prime, but if you still do, the valuation of every agent increases. Is that?
Wait, I didn't get your question.
The I is the original intent and I hat was the converted.
Yeah.
So in I hat, suppose there is suppose Alice is getting some value k. And then it improves.
Yes, the value would improve because every good in their bundle is improving in some sense. Okay. Now let x minus I, now some notation that x minus I is the set of all goods that agent I did not get in the original instance, and x hat minus I is all the goods that agent I did not get in the ordered instance. Okay. So since xi dominates x hat I, it means that the total value of xi is greater than or equal to the total value of x hat I. And that means that the value of x hat minus I is less than or equal to the total value of x minus I is at most the total value of x hat minus I. Okay. This means that when we go from the ordered instance to the original instance, according to agent I, the total value of the goods that she did not get is reducing. Okay.
Yet we are crucially using additive.
Yes. Okay. In fact, we can show something stronger. We can show that x minus I is dominated by x hat minus I. Okay. Now, this lemma is a little tricky to prove formally, but the basic idea of proving it is the same as the previous lemma. Okay. So hence we get a mapping from the ordered goods to the original goods such that when we go from the ordered instance to the original instance, for agent I, every good in her bundle is becoming better, and every good in the other agent, all the remaining goods are getting worse. So now this already seems to imply that this is somewhat fair, that if whatever I have is if an allocation is EFX according to me and all of my goods are getting better and all of the other goods are becoming worse, then it should be fair. So let's see why is the result, why could the result not be EFX? So this is what, so let's take an example that we have an allocation x hat and all these numbers indicate the values of the items according to Alice. Okay? So Alice gets two goods of values 28 and 4, and Bob and Charlie together get these 5 goods of values 30, 26, 5, 2, and 1. Okay? I've arranged these in decreasing order. Okay? Now consider the allocation x. So this is an example of what the output could look like. And so here we can see that Alice's values for her own goods is increasing and her value for the other agent's good is decreasing. Okay. But here we've not seen how the goods are distributed among Bob and Charlie. So something like this could possibly happen, that according to Alice, uh, Bob's bundle is like one of Bob's items is decreasing in value very sharply, but Charlie is gaining a lot. So you can think of it like this, that when the picking sequence was there, according to Alice, Charlie got lucky because Bob only picked up very bad items. And for this kind of a reason, the output may not be EFX. You can show that there is some other allocation Y that does not suffer from this problem. So let's look at a different allocation where let's say this kind of an allocation, that the goods of values 28 and 2 go to Bob, and goods of value 26, 4 and 1 go to Charlie. In this example, according to Alice, both the other agents' goods are getting worse. In fact, we have the same mapping here in these two examples, and this is not a coincidence. So when so basically, this is how we construct an EFX certificate, that you construct a table like this, that according to Alice, what's happening to the other remaining goods, and then you just look at the allocation X hat, and then you the goods that you give to the other agents is just based on this mapping here. So if you do this something like this, then you would get an epistemic EFX certificate for the allocation X. Yeah, so that is basically the algorithm. Since we've shown the presence of an EEFX certificate, this would imply that the allocation is epistemic EFX. Yeah, I mean, this is not a formal proof. But
The original tag might not suffice, but how do you change it?
yeah, so this is X hat, and this is something. This is what X looks like. Okay, suppose this is what we have. We got X hat and X from our algorithm, and now our task is to construct a certificate for Alice. Okay. So to do that, we note down the mapping that according to Alice, the good of value 28 is mapped to a good of value 30. Good of value 4 is mapped to a good of value 5, and similarly, this is the mapping that we have. So this is the same as the mapping that we showed from the two lemmas, that according to Alice, the goods in Harun Mandal are becoming better and the remaining goods are getting worse. Okay, so we just apply this kind of mapping to the agent's bundles. So let's say X hat is something like this, that Bob is getting goods of value 30 and 2, and Charlie is getting goods of value 26, 5 and 1. Now we just apply this mapping. In this mapping, 30 is mapped to a good of value 28. So we just give Bob a good of 28 and a good of value 2. 2 is also mapped to 2. So we just apply this mapping, and that will give us a new allocation value. So that was the algorithm. So today what did we see? We looked at some notions of fairness and their limitations. We saw that MMS does not exist and existence of EFX is unknown. We also looked at the instability of EFX. And then we looked at the notion of epistemic fairness and the mind your own business principle as ways to possibly circumvent those issues. And we looked at polynomial time algorithm for epistemic EFX and 2x3 MMS.
If you don't care about the running time, initial time, it is possible to get something EFX plus MMS or some better bound than 2
Yeah, that was a problem that I worked on for a long time, but I couldn't get anything better. Yeah, MMS was not. Yeah, but we could maybe get some like better than 2x3. So our algorithm is not limited to additive valuations, but also works for a class of valuations called cancelable valuations, which generalizes additive valuations to some other, and also a few other valuation classes. Okay. Yes. For chose, I'm not sure. I think I did look into it, and I guess I had a counter example that MMS need not imply epistemic EFX, but I'm not sure. So I won't really go deep into this result, but the sketches that. Huh? Yeah, this
requires some changes.
yeah, this algorithm that we saw that also works for chores. So
Yeah.
even for chores, we get epistemic EFX plus.
Right.
Yeah.
What is the class like? The submodeler is still open.
Yeah, it's still open. Yeah. For the proof that epistemic EFX implies 4 by 7 MMS follows almost directly from previous work. So we not really did much. We just noticed that this result is like almost there. Yeah, we can also get epistemic EFX plus 4 by 3 MMS for chores using the same algorithm, like using a similar algorithm in the same paper of Burman and Krishnamurthy.
Why is 2 by 3 not becoming cumulative?
Yeah, that's for chores.
It's a min-max problem. You want like an upper bound rather than a lower bound in the case. You want your cost for the choice to be at most large. So it's typically expressed as a number within point.
Yeah, but like.
But it's not 2 by 3 should become 2 by 2. Oh, like goods and chores are not symmetric. Years of pain and misery have taught me. It's not like there's many open problems for like EF1 plus PO, which chores is a big one.
So, what techniques you use this computing to be used to prove the equivalence of that ABC equal to 0 DI of A is greater than DI of B. You showed this relation.
Oh yeah.
Does that use any of existing?
So I didn't for that to prove that I didn't. It's not relying on like some heavy machinery or anything. It's just like the proof is elementary. It's the kind of proof that's easy to understand because it doesn't use anything, but it's not so easy to come up with. Yeah, it intuitively seems fine, but like proving it formally is you need to do right kind of case analysis, something like that. Yeah, also for the special case of ordered instances, we can get EFX allocation, but when we don't have ordered instances, then we get epistemic EFX. So question is that can we interpolate between these two notions? And the answer is yes. That for certain. So in real world instances, it's unlikely that all the agents will value the items in the exact same order, but this could still have some correlation between the values of the items. So we defined a notion called alpha correlated valuations, and we showed that for such cases we can get epistemic EFX plus alpha EFX using the same algorithm. So we say that so let's say if I value something, so let's say there are two goods and I value this more than this, then if I'd say that your value, then you would value this at least, then you would value this at least alpha times more than this, the value of this, where alpha is somewhere between 0 and 1.
This is some sort of a assumption of the valuation.
Yeah.
Like the sort of notion that we can correlate with that, sort of assumption of the valuation.
Yes. Like I'm asking more generally in this area, are there assumptions or relations that you can make?
Identical.
Yeah, that is like
Yeah, certain classes, some module like data RAM.
Uh, so existence of EFX allocation is a big open problem, and whether epistemic EFX exists for non-additive valuations, that is another good open problem. Another good open problem is trying to get epistemic EFX with other notions of fairness. Like in addition to epistemic EFX, if we can get EF1 or alpha EFX or alpha MMS. So we already have 2 by 3 MMS. I and Professor Jugal tried to get to improve upon 2 by 3, but we have not succeeded in doing that. Getting a counter example for EFX plus optimality. I mean, we already have one, but that involves some goods having 0 value, something of that sort. Yeah, it would be a good example if where all goods have positive valuations and you have a additive valuation. Yeah, whether we can get some efficiency notion like optimality or Nash social welfare in addition to epistemic EFX. Also, there are other settings like chores and mixed mana that we can consider.
I had asked questions for all any fairness question. Epistemic version is by default a top.
Slide.
It was what is stopping Pareto improvement? How would it be?
Because if you do a Pareto improvement, then the value of your own bundle would increase, but the fairness notion.
After getting rich.
Yeah, that's it. Thanks a lot. Yeah.
So I have one question. How is not clear about can you both that slide where you explain that
Alpha EFX. The definition. Okay. It will take a while.
yeah. So you are saying that you can do problems that particular number 5 minus 1 So so you want to sequence the ratio between two consecutive number converges to the same.
Yeah.
So is there any correlation between
I'm not sure about that. So the algorithm for this is quite different. They maximize the Nash social welfare, and if you do that, then you get this.
What is the correlation?
Yeah, I think it's. Sure, I think I once looked at a counter example for. I think they were trying to show that the Nash social welfare need not be an EFX allocation. In fact, it need not also be an alpha EFX allocation for large enough alpha. So they created some counter example that was parameterized by something, and then to get the worst possible counter example, they tried to optimize it. And somewhere there was a quadratic equation, and when you solve it, you get this value. And the speaker.
Yeah, so yes.
Nice.
other comes around.
Standing on the stage, sitting in my